Get started. Welcome back. Hope you had a relaxing weekend before the first week of classes. Does anybody have any questions before we get started? Questions? Any questions? Okay. Uh, what's new on Apple Pencil? All right. So a couple of things. One is we will have a class for the honor section this Thursday, so come to the class. I think last week I said no class, but I made a mistake. There will be a class this week. Second thing is waitlist people most likely will get in, so don't worry if you're on the waitlist, you will get in. Third thing is on Thursday, I need to go to Anaheim in the morning for a conference. I'll drive back hopefully in time, but I might be like 10 to 15 minutes late. So if you come to the class and you don't see me, just wait for we're probably gonna start at like 12:15 or something, okay? Sorry about that. There's something this is just other commitment that I couldn't move it at all. But hopefully there won't be enough, lots of traffic or enough traffic. So I'll be here in time. But if I didn't, just keep that in mind, okay? Yeah, and then I see most people already enrolled on CampusWire. Great. If you're not enrolled on Gradescope, don't worry. I'll reran the enrollment again, and those specifically people are dropped or gotten recently, they're not enrolled yet. And we're gonna do that. One more thing I wanted to say. What was it? I think that's it. If I remember, I'll talk to you. Any questions? We good? All right. So last time, if you remember, we were talking about. I was making the case that we are making computers much faster, right? And then I started with this that one key reason is the technology itself. And we started talking about this kind of observation, which became some sort of a law, which is not really a law. It's more of like an observation that one of these prominent researchers at the time was predicting that the number of transistors is going to be doubled almost every 2 years. And in fact, it did that. That thing did happen, and it actually followed very nicely over many, many years. Although there are lots of discussion on, the Moore's law is ending or it's already ended. So depending on who you ask, different people might say different things. But there's just general notion that Moore's law is slowing down. But the important thing about Moore's law is, as I said, the main thing about Moore's law and what kept Moore's law going was the fact that we could build transistors with the reduced cost as we move to another technology. And these other things, these other important metrics about the transistors, which is followed by what we call Dennard scaling law, is also kind of follow the same pattern. If you remember, I said that essentially the main thing about technology is that the size of the transistor is reduced by half, which means that each dimension was reduced by 0.7 roughly. And we're kind of trying to see what happens when we do that. So we start talking about the voltage, and we show that the voltage decreased because we want to keep the electric field constant. Since the distance is reduced, we don't need more voltage anymore, so we can reduce the voltage. Good thing about reducing the voltage is that you spend less energy and power, as I'm going to show you in the next slide. Then we talked about the delay and say that, okay, another great thing about reducing the technology, going into the lower technology is the fact that the delay is reduced. And delay is reduced because essentially the distance is reduced, right? So the speed of the electrons are the same, but now they need to kind of follow a smaller distance. As a result, the time reduces, right? And then when the delay is reduced, 1 over delay is also increased, right? So the frequency increases. As frequency increases, it means that we can clock faster. As we can clock faster, it means that we can kind of compute faster, right? So that was also another great thing. And another great thing was the capacitance also reduces. The reason for the capacitance is that the formula for capacitance was like this constant K, which is kind of a material-based design, times the area divided by distance. Since area is reduced by a factor of 2 and distance factor of 1, essentially the overall capacitance is reduced by a factor of 1, right? So it's reduced by 0.7% as well, which means a 30% reduction. Good thing about capacitance, think about capacitance as a load, that if I want to kind of turn a transistor on or off, I need to kind of charge or discharge a capacitor. So if the capacitor is smaller, it means that it requires less energy, less power to load the capacitance, which is also a great thing. Okay? So these are all great observations, and if you actually plug them all together in terms of power and energy, you will see that if I put like 0.7, 0.7 times 2, and then the increase on increase on the frequency, you will see that the power also kind of reduce by a factor of 2. So this is like 50% reduction in power consumption we're going to observe. And then since the number of transistors is double, if you kind of say that, okay, the overall power is the number of transistor times the power per transistor, then essentially the overall power stays the same, because this is increased by a factor of 2, but this is reduced by a factor of 2. So they kind of cancel each other out, which means that the overall power consumption of my chip going to stay constant over one generation to another generation. Even though I packed twice as much transistors, even though I increased the frequency by 30%, but still I managed to have similar power consumption. That's great, right? And by the way, this is what we call dynamic power. And this is important because this is just the power for switching. It's not power for just a regular static power, which we're going to actually talk about later, okay? So, and then the energy is kind of like, following the same pattern, all right? Is this clear? Anybody has any questions of how we come up with this number? Yeah. Turn the volume up, okay. Is it better now? Or does it change? No? Think maybe this is not working. One, two, three. No? I'll try to speak a little bit louder. Any other questions? Yeah. If the power is the same, what was the second part? Well, the point is showing that the power, so consider this, that if the power wasn't staying the same and it was growing up, then we couldn't like pack more transistors in the system, right? If the power was twice as we move from one generation to another generation, then we were kind of limited by the amount of power that we could pump into the system. Does that make sense? So what I'm trying to say here is that power is not an issue when we are moving from one generation to another generation, because the overall power consumption stays the same, even though we are adding more and more transistors. Yes, of course, more transistors is better, right? Because you have more things, you can do more things with it. Okay, any other questions? All right. So that's kind of like it with the technology. The main message I wanted to send was, for the longest time, we could actually increase the number of transistors in our systems. We can make them faster without really any impact on the other aspects of the system, okay? Although this is changing a little bit. I'm going to talk about that later in the lecture. So this is kind of like, if you remember this graph that I showed you last time, this is kind of like what's happening at the beginning. Like this big jump in the first 10 years or so is mainly because of these technologies, okay? But then things start to kind of like speeding up significantly. So it's not just the transistors that gives us the speed up. It was also the other factor that helps us to significantly increase the speed of our computers. And that was like the architectural and organizational ideas. And these are the main things that we're going to talk about in this course. So these are more traditional things that we did in order to make our computers much faster. This includes things like pipelining and parallelization and caching and all those stuff. And as you can see, what used to be 25% per year, now it's 52% per year. And actually, numbers shows that if we didn't have this improvement, we had this today with just the technology, we would have had computers that are 25 times slower than what we have now. So that's kind of the impact of the computer architecture on the system. Okay. So what are those? So we're going to talk about that. But there's actually a little bit more into this graph. Yeah. No. So the question is, when I'm talking about improvement, am I talking about the density of transistors? No, I'm talking about the latency, like how fast can we compute? Okay. So this graph, the y-axis in this graph is performance. So how fast computers are. And they're normalized to this very first computer that we have here. So when we say 10 times or 10,000 times, it means that it's 10,000 times faster than the original computer, like the first PC that we have. So if you run the same application in both, computers today are going to run that program 10,000 times faster. All right. So we kind of nicely managed to have this 52%, 50% per year improvement until 2003, okay? 2003 was when there was like a big turning point in our system. Does anybody know what happens around that time? What's that? Oh, you were born, yeah. You are the cause of... That could be one reason. Any other suggestions? Yeah. Say it again. The dot-com bubble, okay? That dot-com bubble was actually one of the outcome of the computers got much faster. So actually everybody now could use it and can do things with it. So dot-com bubble was actually the outcome of this computer getting faster, and kind of started somewhere here actually in late 90s. And again, you can clearly see why dot-com become a big thing, because we had much faster computers. Any other suggestions? Someone raise their hand? Yeah. Yes, the multi-core systems, came. But what was the cause of the multi-core system? So there's this thing called Powerwall. And this was a big thing in early 2000 that, I told you that the kind of power stays the same as we move to another generation. What happened was that, I kind of lied. The reason for it is that the overall power is two things. It's the dynamic power plus what we call the static power, okay? Static power is the power that when your transistors are off, are not switching, this is the amount of power that they consume. And when the transistor is off, the overall assumption is that the static power is very, very, very small, okay? As a result, this thing stays the same from one generation to another generation, so we never worried about the overall power consumption. What happened, though, was that as the transistor is getting smaller and smaller, then this static power gets bigger and bigger. The reason for it is because of quantum mechanics, because there is this, so think about, like, if the one electron wants going from here to here, there's some sort of a barrier that they need to jump over. And if the distance is large, this barrier is large, okay? So they cannot really jump. If the distance is small, they can kind of squeeze in, so they can actually go underneath. There is like lots of physics behind it that I'm not going to talk about. I honestly don't know much about either. But generally, this leakage power, this static power, gets very significant as we move to a lower and smaller transistors. And the bad news is, as we are going to even smaller technologies, this static power grows. Okay? So what happened during 2005 was that was kind of the turning point. That was the transistor size that the static power gets so huge that we could no longer keep the power constant. So as we add more transistors, the power consumption shoots up at the point that we couldn't really power the transistors anymore. Intel called this power wall, which means that we could no longer add more transistors because as we add more, we need to power it more, and we didn't have enough power. In fact, what happens is that they found that the amount of heat that is generated by pumping more power going to be so high that the transistor is going to be as hot as a rocket nozzle. That's how hot it can get if you really wanted to power up the transistor. Okay? So that was the big issue because we no longer can pump and add more transistors to our system and kind of follow the Moore's law. Remember, Moore's law was saying that the number of transistors has to double every 2 years in order for us to keep kind of like increasing the performance. Okay? So what happens in 2005? What happens after this? That there was lots of kind of negative thinking about that, oh, this is the end of the semiconductor business. We can no longer have faster computers and so on, until the multi-core thing happened. So the idea of the multi-core was that, okay, I don't need to make one core bigger, but what about I add another core next to it, okay? In other words, I don't need no longer to add bigger and more transistors per core, but I can have multiple cores. And if I somehow can distribute the workload in these multiple cores, I can power them separately, I can heat them separately, I can cool them separately, and so on and so forth. So I can get the speed up from the multi-core. If I can kind of nicely distribute the work to 2 cores, it's as if I have one large core, right? So this is what we kind of what we call the multi-core era, which we're still kind of in it, that it's no longer just one core, there's actually multiple cores. So we start with 2, but these days we might have like many number of cores. Like high-end servers have, let's say, 64 cores, okay? So in the second half of the class, we're going to talk about multi-core and how multi-core works and what are the challenges with multi-core, okay? Questions? All right. So this was here. So we actually managed to kind of dodge the bullet in some sense, but it slowed down a bit because we couldn't be as aggressive as we used to be, right? So this is what when we are talking about, oh, Moore's law is slowing down, we're kind of talking about these things, okay? But then things get even slower, and this is kind of like 10,000-ish. And the reason for this is that we had limited amount of parallelism. Remember, for multi-core to work, you need to distribute the work into multiple cores. In other words, you need to be able to do things in parallel, okay? But the problem is that your workload doesn't have parallel work all the time. And this is what we call the Amdahl's law. Amdahl's is another famous scientist in this area. Essentially, the Amdahl's law is this very simple thing, is that if I have, let's say, S number of cores, okay, the amount of speed up I'm going to get, and speed up means the time it takes for doing things. So let's say, for example, I have 2 different setups, configuration 1 and configuration 2, okay? So let's say I run one application and it takes T1 time. I run another application and it takes T2 time. The speed up is going to be calculated based on T2 over T1, okay? Which means that if actually the other way around. T1 over T2, okay? Which means that if I make some changes and make C2, if let's say my speed up is equal to 2, means that my system runs things twice faster, right? So if T2 is smaller than T1, then I'm going to have positive speed up, more than one speed up, right? That's what you want, right? So you want, for example, let's say if C1 is a single core, okay, and your C2 is, let's say, a dual core, okay? So ideally, you are expecting to see a speed up of 2, right? Because I have 2 cores, I can parallelize this twice, so I'm going to get twice as fast computer, right? But in reality, this is not the case because you are essentially limited by the amount of work that you can parallelize, okay? Think about moving, right? So if you have 10 people helping you when you're moving from one apartment to another apartment, doesn't necessarily mean that you can do your moving 10 times faster. Why? Because yes, there are parts that you can parallelize, so like everybody can kind of move the boxes all together and all that things. But let's say, for example, you have a bottleneck. Let's say, for example, there is a small hallway that only one person can go in and out at once, which means that you're essentially limited by the part that is going to be serialized, okay? So to make it more formal, let's say that P is the part that you can parallelize, and S is the factor for improvement, how much you can parallelize things. So for example, if you have 2 cores, S could be equal to 2, okay? So the amount of speed up you're going to get from parallelization is 1 over 1 minus P plus P over S. In other words, the part that you can parallelize is going to be divided by factor of S. You can make that part faster S times. But the part that you cannot parallelize not going to benefit from how many cores you have, okay? Think about reading from input and then do some addition multiplication. Reading from input doesn't matter how many cores you have. You're always bounded by how fast you can read things from like your I/O or your memory and so on and so forth. So if you have 10,000 cores versus if you have 1 core, the time it takes to reading the inputs is exactly the same, and that's this part. But let's say you want to add. So now if you read all the inputs and you have many, many cores, you can add a lot of them at the same time, and this is this part, okay? So I can speed up the part that I can parallelize, but I cannot speed up the part that I cannot parallelize, okay? So in other words, my speed up is kind of be limited, but not only how many cores I have, but also the type of workload that I'm going to get, okay? And as you can see here, we still can make things faster, but at much slower rates. And the reason for this is that not all the workload has parallel things to parallelize all the time. Does that make sense? Questions? Cool. So as I said, this is what we call the limited amount of parallelism available because of the Amdahl's law. All right? And essentially, we are now at this kind of age here, and it's kind of like, this is like ended in 2018 because this is a figure that we got from the book, which was published in 2018. But we are kind of following the same pattern at the moment. And this is the age of what we call dark silicon age, okay? The reason that it's dark silicon is that I told you that I can add more cores to my system. And assuming that there is enough parallelism, I can actually make the system faster, right? But again, there is a limited amount of power that I can pump into my chip, although I can like separate the cores from each other. But again, the amount of power required to keep the entire system powered is a limiting factor. That's why we call it dark silicon. So if you think about your silicon as kind of like system with many, many cores, there's actually an interesting paper that shows that large part of your chips gonna be not powered up because we have limited amount of power. In other words, although on paper I have lots of transistors to use, in reality I cannot keep all of them switched all at the same time because it requires lots of power, okay? So this is what we call dark silicon, and again, this means that I can no longer add more and more cores to the system unless I find innovative way of like powering the system up and so on and so forth. And this is the era that we are living in right at the moment, okay? So now the question is this it? Is this the end of kind of like this kind of conquest? And the answer to that is no. One big thing is AI, right? So what is happening is that we found that, okay, forget about having multi-cores and like, Amdahl's law and all those things. What happens is that now we have this killer app that is perfect for parallelism because essentially it's at the core it's a matrix multiplication. That what I can do is that I can throw a lot of core at it and I can do a matrix multiplication really fast. And then another nice thing is that now I can have many layers of this matrix multiplication. I can do all those things also very fast. So what happens is that we are essentially transitioning with what we call general purpose workload, that is your regular applications, I don't know, your browser and your Microsoft Word and your Google Doc and all those things, to what we call AI workloads that are inherently very, very parallelized. You can actually run things much, much faster. So what is happening now is that what we used to have kind of these general purpose processors that was kind of like very flexible, can run all the things. But now we realize that we also need other types of architectures. So essentially, we start emphasizing a lot on GPUs, and then we start looking at what we call domain-specific accelerators, things like TPUs and so on and so forth. These are very narrow in terms of flexibility. They can only run particular things, but they can run those things very, very fast. That's why if you look into your computers these days, you will have a GPU, you will have a neural engine, you will have a particular coprocessor for your cryptography, for your video, and all those things. So it's no longer just one big CPU. It's actually now what we call an SoC, which has a CPU, has a GPU, has an NPU, it has a bunch of all these other little cores, and so on and so forth. So now we are kind of like making more and more specialized design. And at the very end of this course, we're going to talk about that kind of part of the design. Okay? Questions? Yeah. Uh-huh. Uh, so the question is that I mentioned that the big problem is the energy and cooling factor. How does this cooling factor is not an issue with something like AI? So what is happening is that you still have similar amount of cores and similar amount of transistors. They're just more efficient at doing their job. So in other words, they can run, for example, matrix multiplication much faster than an equivalent of that in a CPU system. So you're not really introducing more transistors. You are kind of just making it very specialized so they are getting better at doing the same thing. Yeah. Yes. So the question is that the speed up is coming from the fact that you're only having one thing, like you are having multiple things, but each one are specialized in one particular type of workload. And they can do that very well. Okay? Think about similar to what happens to our communities, right? So like people in the past used to know lots of things, but now everybody's kind of know one exact thing. So now they're specialized in one thing and they can do that one thing very well, right? So that's same idea. All right, so kind of like quick takeaways to kind of finalize this discussion. So we managed to historically double the performance every 24 months. We kind of used various different tricks in order to keep that pace, including multi-core specialization, different techniques, and so on and so forth. A big thing is that microarchitectural tricks, that is kind of the main focus of this course, helps us to make computers 25 times faster than what should have been. And that's very important. So it wasn't just the technology. It wasn't just that we can put more transistors. It was also we managed to put these transistors in a more strategic way. Okay? we hit the power wall in 2005. We are now experiencing the dark silicon and end of multi-core. But what we're going to see is that we are continue kind of going further. I'm going to talk about like what comes after this. So kind of like we're going to look at the future as well. But that would be week 10, sorry. So we're going to talk about, okay, what happens next, right? So what is the next big thing that we are expecting to see? So that's kind of it with lecture 1. Any final questions about these? All right, cool. So let me go to the next one. All right. So in this second module, and by the way, I'm going to call these modules since that it's going to be overlap between lectures. So today the next thing I want to talk about is about the ISA. If you remember, I told you that there's kind of like, the intersection between software and hardware and where kind of the computer architecture begins is the instruction set architecture, right? So we already talked about this. And as I will say that we're going to talk about what goes beyond what we have already. There are 3 main things that we're going to discuss. This is what we call more. There is another one called more than more. And there is also what we call beyond CMOS. So we're going to talk about that in week 10, okay? But let's talk about instruction set architecture. I gave you an example last time, and I'll show you that we have this big problem of compatibility between software and hardware. There are many different languages, there are many different companies, there are many different versions of the one company, and so on and so forth. So how do we maintain this compatibility? And we said that the answer to this is ISA. Essentially, everybody agrees on a list, and everybody kind of adheres and stick to that list. And hardware designers will implement that list. Software designer will provide tools that generate and translate software to that list. This way, we're going to have a working system, okay? So we're going to talk about what is that list, how do we create this sequence of instructions, what are those, and why is it important, okay? As I said, the ISA is the contract between the software and hardware. Typically, the ISA has this thing called programmable visible state, which in other words is the registers and memory, which I'm going to talk a lot in the rest of this lecture. And then some semantics about the instructions. For example, what does this instruction do, right? What is the time life of this instruction, and so on, okay? IBM 360 was kind of like the first line of machines that has the idea of like ISA. And then there are many possible implementation for an ISA, okay? So for example, AMD, Intel, they all have processors that all runs x86 as their ISA, but they have many different versions. So when we say an ISA is, let's say, x86 or it's ARM or RISC-V, doesn't mean that the underlying microarchitecture is the same. Even different companies have very different implementation of the same ISA. Next week, we're going to talk about the microarchitecture and how we implement this ISA. But just keep that in mind that there is difference between microarchitecture and the ISA, okay? The very popular ISA these days is the ARM core, the ARM ISA. The reason for it is that it's very efficient. It has very nice tool chain. So many kind of cell phone and embedded systems and mobile systems are mainly using ARM ISA. So this includes Samsung, Qualcomm, Apple. They all have ARM ISA as their underlying ISA, okay? What we're going to focus in this course is RISC-V ISA. RISC-V is also a standard ISA. It's on the rise. And let me see. Okay. Yeah, it's an open source RISC-based ISA. I'm going to talk about what is RISC and what is CISC. It's mainly designed in early 2010 in Berkeley. The reason it's called RISC-V is that this was the 5th generation of the RISC design that they had. And RISC-V has different extensions and different models. We're going to focus on what we call the base model. So RISC-V I. This is the version that we're going to focus on, and we're going to focus on the 32-bit version. I'm going to explain what is the 32-bit and what is the base. Okay, let me go back to the previous slide. So when we are designing ISA, we usually have a strategy in mind. Okay, so for example, if we want to have a risk-based design, which is the focus of this course, we typically have what we call a hardwire and pipeline design. If we have a CISC-based design, which is what x86 is all about, we usually have what we call a micro-coded design, and so on and so forth. I'm going to talk about these different differences later in the course. But what we're going to focus is that we're going to focus on risk-based ISA, and we're going to talk about a design that is kind of hardwired and pipeline. But keep in mind that there exists other ways of designing a RISC-V, designing an ISA, including the VLIW or virtual machine base, and so on and so forth. Okay, we're not going to mainly talk about them, but just keep in mind that they exist. Okay, if you have time at the end of the class, we might talk about them. All right. Another thing to keep in mind is that there might be different microarchitectural style for a given risk for given ISAs. So for example, Ivy Bridge, which is like a famous version of Intel, was using pipeline hardwire, although it was kind of like, it was a CISC-based design. So it should have been a micro-coded based system. Okay? So just main thing to remember is that there are different design methodologies. Okay? Each one kind of have different goals and different pros and cons. What we're going to focus in this course is a risk-based hardwire pipeline design. Okay? And then don't worry if you don't know anything about any of these yet. I'm just trying to kind of like make it smaller so that you can understand the differences first, and then we're going to talk about what it is. All right? So what is RISC? RISC stands for Reduced Instruction Set Computers. Okay? The alternative to RISC is CISC. And the difference between RISC and CISC is that CISC stands for complex. Okay? So RISC is reduced, is simpler design. CISC is more complex. And as you remember, I told you that most of the systems, including ARM and RISC-V, are RISC-based. But the famous examples of CISC is x86. Okay? So what are the differences? The main difference between RISC and CISC is the size of the instruction. Okay? In RISC, all the instructions are exactly the same size. For this class, we're going to focus on 32-bit version, which means that all your instructions are exactly 32-bit. Okay? But CISC is variable, which means that some instructions are 16, some instructions might be 32, some instructions might be 64, and so on and so forth. Okay? So that's a big difference. There are pros and cons for each design. The good thing about RISC is that it's simplified, so the decoding part of your instruction set and microarchitecture is much simpler. But on the other hand, you have less flexibility in terms of things that you can do. Okay? The second thing is that RISC is usually very simple. It's one-by-one operations, which means that I only do add, or I only do subtract, I only do XOR, I only write to the memory, or I only read from the memory, and so on and so forth. So typically, each instruction is just one logical operation. CISC is not that. So CISC is very complex. Sometimes you do comparison and then writing it to the memory, when sometimes you multiply and add at the same time, and so on and so forth. So the difference between RISC and CISC is simple operation versus more complex operations. And overall, the complexity of CISC and RISC is the main difference. CISC is much more complex, but if you can get it right, you probably can extract more performance out of it. But in most cases, people like RISC. Kind of think about quarter system versus semester systems. Quarter systems is considered as CISC. Semester system considered as RISC. You might argue that CISC is better than RISC, but everybody knows that RISC is better than CISC. Okay, so that's kind of the idea. If you want to know more about RISC and CISC, this is a good kind of like a quick blog post about these. You can take a look at that. Uh, uh, as I said, widely used RISCs are MIPS, ARM, PowerPC, and RISC-V. This is kind of like the majority of anything that is not AMD or Intel is essentially RISC at the moment. And that's why we're going to focus on RISC. But keep in mind that many things that we're going to discuss here, they are the same for almost all the different RISC-based. So we're going to focus on RISC-V, but many principles are the same for ARM and MIPS. And also many principles are the same for RISC and CISC, although there are some tiny differences between them. Okay? Questions so far? Okay. So let's go dive a little bit deeper into this ISA and how do we design ISA. To answer how do we design an ISA, we have to think about how do we run programs on a computer. Okay. A very simplified assumption about the computer is what we call a stored program computer. Okay. Stored program computer, or a von Neumann model of a computer, is this: that essentially think about CPU, or generally the processor, as this machine that has kind of a memory, which we usually call instruction memory, IM, that takes instructions line by line. Okay, so think about every instruction is one line of memory, and then you have the CPU here. Okay, that all it does is essentially taking one of these instructions, execute it, write the results back to some memory, and go and grab the next instruction and run it, and so on. So essentially, the stored program or machine is this machine that takes one instruction at a time, executes it sequentially, and goes to the next one, and next one, and next one. Okay? That's what we call a stored program, or von Neumann model. Okay? The alternative to von Neumann model is what we call a data flow system. Okay? A data flow system is a system that doesn't have any instructions. It just goes with the flow of data. So think about something like a MAC, a multiply accumulator, that multiplies two numbers and added with some partial sum that it has, and store the results back to this. Okay? So there is no notion of instruction here. As the data is coming, as these two data like X and Y is coming, this two will be multiplied and added with the previous results and will be saved back into the partial sum. And it keeps happening. You can synchronize this with some form of a clock, for example. So you can add some form of a register here to make things nicely synchronized with clock. But there is no notion of instruction and next instructions and different commands. Okay? And this is how we actually usually design our accelerators. Those domain-specific accelerators I talked to you about, these are how we design them. But the main CPU and the GPU, there are these von Neumann machines that what they do is that they take one instruction, they see what it is, for example, whether this is an add or a subtract or a multiply and so on and so forth. They execute that, they save the results, they go to the next instruction and repeat. And this thing happens over and over until you finish the program and you run another program. Okay? So how do we actually design this? We typically have what we call a memory and a CPU. Okay? A memory and a CPU. That's the main two things that we're going to have in a stored program machine. The memory could be two parts. Could be a data memory or an instruction memory. The data memory is where you store your temporary data. Your instruction memory is where you save your instructions. Okay? Most designs combine the two, so there is no two different memories. There are one memory that stores both data and instructions. Typically, we kind of like put it into sections. So we have like a data section, we have an instruction section, we have other things like stack and heap and so on. But you could have other designs that has a separate physical data memory and a separate physical instruction memory. Okay? we typically store them in a linear fashion, which means that instructions right after another are in sequential order of addresses. Addresses could go up or down. Typically for this class, we usually go down. So like the 0 address is here, and we go down this way. But it could be also going up. It doesn't matter. And then what we do is that we keep track of which instructions we are running. We read that instruction, execute it in the CPU. Then we go to the next instruction, read that, execute it in CPU, and so on and so forth. In order to keep track of the current instruction, we typically have a register called program counter, or PC. PC always points to the current instruction. This is the instruction that we are executing. Once we go to the next instruction, we have to increment our PC to the next instruction, okay? And again, so essentially, execution is basically this, that PC finds the current instruction. We bring that instruction from the memory, which we call it fetch. We execute that instruction. We essentially update our system, our state, and then we write that state back into the memory, and we repeat this process over and over again. Okay? Very simple. Probably all of you already know this. Okay? So based on this, we're going to build our system. So essentially, we need a sequence of instruction line by line that is clear what they do. And based on that, we're going to design a processor that reads this instruction and execute them one by one. Okay? So when we are understanding this kind of sequence, now the question is that we have software, which is what we call high-level language, or HLLL. We need to now translate this into a sequence of what we call assembly. Assembly are those instructions that are understood by hardware, okay? This next step after kind of translating software to sequence of instruction is that we need to do three things. We need to generate what we call a binary of this, which essentially the assembly needs to be translated in a sequence of zeros and ones. We're going to talk about this next lecture. Then we need to somehow put this into the instruction memory of the hardware, so the literal movement from, let's say, your computer to the hardware. And then we need to then actually run this. And this will be the discussion we're going to have in the next 2 weeks of how do we do these two other steps, okay? So let's actually talk about this assembly design and how do we design this assembly, and then how do we translate this high-level language into this assembly, okay? So if you think about an instruction, generally instruction looks if you want to simplify this, looks like this. It has two parts. It's a command part, and there's an operand part, okay? As I told you, we are focusing on RISC-V 32-bit version, which means that each instruction is exactly 32-bit, okay? RISC-V also has a 64-bit version, which instructions are 64-bit. RISC-V also has what we call a compact version, which is instructions are 16-bit, okay? What we are focusing here is that everything is 32-bit, okay? So let's talk about these two different things, commands and operands. And let's start with operands, okay? So for RISC-V, you have three possible operands. You will have registers, you will have immediates, you will have memory, okay? Registers are the simplest one. Registers are this small storage unit inside the processor that holds temporary values, okay? The good thing about registers is you can access them very, very fast. The reason that they can access them very, very fast is that they're very small, okay? So you use this kind of like holding temporary values. The main difference between a register and a memory is that registers are much more smaller. And generally, in designing hardware, smaller means faster. If you make things bigger, they get much more slower, okay? And the important things about registers is that they can be seen by software. In other words, you can actually say that I'm going to write into this register or that register in assembly language, okay? And I'm going to talk about what does it mean that things are observable by software later, okay? And in modern ISAs, we typically have somewhere between 16 to 64 general purpose registers, okay? The reason for this is that we want to keep them small. okay? If we make them, let's say, 1,000 registers, then it's not going to be small anymore. They're not going to fit into a small chip, which means that it's no longer be fast enough, okay? So main thing is about registers is their width, okay? How large each register is. We have, let's say, 32 registers, but each register also has a width. In this class, we're going to focus on 32 version again. So all of our registers are 32-bit as well. But keep in mind that if I have bigger registers, it means that I can do more things in parallel. Remember, I told you that parallelism is the main thing that gives us speed. So if I had bigger registers, I could have add more data all at the same time. But there is a trade-off. Bigger registers means more power consumption, more area, and all those things. So that's why you need to kind of decide what is the size. So that's why, for example, you have 32-bit machines, you have 64-bit machines. More powerful systems are 64-bit machines. Less powerful systems are 32-bit machines. If you go, for example, to your, I don't know, watches or smaller embedded processors and so on, this could be even smaller. Your register could be like 8-bit or 16-bit because you want to save a lot of power. The performance is no longer that important to you. You want to save a lot of power, okay? But good thing about more registers and larger register means that you need to go to the memory much less. And memory is slow, as we're going to talk about. All right? So there is this inherent trade-off between the size of the registers, how fast your system can run because of the size of the registers, versus the amount of power and area that you have. So keep that in mind. Okay? So as I said, low-end registers use the smaller registers, less number of registers. High-performance systems use more registers and wider registers. Okay? In this class and in this design, we're going to have 32 registers. Each one is 32-bit. Okay? 32-bit is called word. Okay? So when we say it's one word, it means that it's 32-bit. Okay? The 64-bit version of RISC-V, which is called RV64, so this, by the way, is called RV32. So the 64 version has still 32 registers, so the number of registers doesn't change, but their width changes, okay? So 64-bit version has 64-bit registers, 32 of them, and we call this double word, okay? So when we say double word or DW, we are referring to 64-bit version. When we say word, means 32-bit version. And then we also have half word, which is 16-bit, okay? Registers in RISC ISA shows as X. So for example, we have X0, X1, X2, and so on and so forth. We have 32 of these, which means that, and we start from 0, so we have X0 to X31, okay? X0 is always 0, so you cannot write to X0. If you write to X0, nothing will happen. It's hardwired to the ground, which means that it's always 0. The reason for this is that 0 is very important for us because we can generate numbers with zeros, as we're going to show a lot. We're going to see a lot in this course. All of the registers are stored in one big array called register file. Okay, so register file is actually a hardware unit that saves all these registers all at the same time, and this is what we call a register file. Okay, and all the registers in RISC-V base ISA are integers numbers. There is usually a separate register file for floating point numbers. We typically have another 32-bit, 32 register for floating, but but floating in general is very power consumption, power consuming. So in low-end processors, we only have integer register file. In high-end systems, we have both integer and floating point register files. Okay? All right, so that's it with the registers. Any questions? All right, let's have a quick break, 5 minutes, come back at 1, and then we can talk about the others. All right, so the next thing is, guys, So let's talk about immediates. I mean, these are like rather simple things. So I'm sure that most of you already know about this in your CS33. So immediates are numbers, are actual numbers that we can use, okay? These are constant numbers, okay? So for example, we can, in RISC-V, we have an instruction like this, that is add I, x2, x1, and 5, okay? So x1 is register number 1, x2 is register number 2, and this number 5 is what we call an immediate, okay? So what this instruction does is essentially add x5, x1 with number 5 and write the results in x2, okay? So that's what it does. The main thing about immediates is they are not necessarily 32-bit, okay? The reason that they're not 32-bit is because they need to fit into the instruction itself. And remember, the entire instruction was 32-bit. And the instruction has a bunch of these other things, including like an opcode and so on that we're going to talk about. So immediate cannot be 32-bit. So it's usually like either 12-bit or 10-bit, in some best cases 20 bits, okay? So when we are adding these two numbers, so for example, if you're adding x1, which was a 32-bit number, to 5, which is, let's say, a 10-bit number, we will have some problems, right? What should we do here? Like, you guys should remember this from your past courses. So if you want to add a 10-bit number to a 32-bit number, what should I do? Anyone? Yeah. Padded with zeros, kind of. Maybe a more accurate answer? Yeah, you extend it and you sign extend it, okay? So you need to extend it, obviously, right? So from 10, you need to somehow go to 32. Once you have 32, then you can add two 32-bit numbers together, okay? So you need what we call sign extension, okay? Sign extension is a process of extending a smaller number to a bigger number. So in this case, for example, from a 10-bit to a 32-bit. And the reason that it's called sign extension is that typically these numbers are sign numbers. So they could be negative or they could be positive. So if I just add zeros, I'm not gonna protect the sign. So for example, those of you who remember in old days that what was 2's complement, typically we have like a sign bit at the end, and then we have just regular bits here, okay? If I just randomly add zeros here, then I'm going to destroy this sign bit. So I have to be very careful about how do I extend this number. And there was sign extension algorithms, probably you heard about 2's complement and all those things. Hopefully you already know what they are. If you don't, it's now a good time to review your notes. In the book, there is actually a good section about 2's complement. The TA this week will also talk a little bit about 2's complement. So keep in mind on those and read those if you don't know how it works, okay? So it's important to know those. Because most of the operation in RISC-V are signed. That's why just padding it with 0 not going to work, okay? So that's it with the immediates. Immediates are just constant numbers that you can use in most of these instructions. Okay? The only thing about immediates is that they need to be sign extended to be 32-bit. Okay? Last thing is the memory. The third operand that we can have in any instruction is the memory. Memories are essentially these values that are stored in memory. Remember, we had data memory and instruction memory. Here, when we say memory, we are talking about data memory, right? So the data that you stored. The reason that you need memory is that you cannot fit everything into your registers, because registers are only 32 of them, only 32-bit wide, okay? So at best, you have 32 times 32 bits you can store in your register file. But usually your data is much, much larger. That's why you need to save them into the memory, okay? So memory is where you can actually read and write from to load and store data from. Memory should be byte addressable, which means that I can be able to read any bytes from the memory that I want. This is for traditional reasons that initially memory was just bytes per byte. That's why any design in memory should be byte addressable. So we should be able to read any byte in the memory that we want. And you will see why this is an important later when we're talking about the memory, okay? So the two main operations for memory is load and store, okay? So if we have the CPU here and we have the memory here, okay? Loading is the process of reading from the memory, okay? So the CPU puts the address, gets the data, okay? This is what we call load, okay? If we read 32 bits, we call load word, okay? We show it as LW. If we read only 1 byte, we call it LB, which means that we load 1 byte. And so on and so forth, okay? So we put the address, we read the data, and typically this process takes some time. Memories are slow, so it takes multiple cycles to read from the memory, okay? Storing is the opposite, okay? So storing is that we have the CPU, this is loading. We have the CPU, we put the address, we also put the data, okay? And then we store it into that address, okay? This is what we call store. And if we write a 32-bit data, we call it store word. If we write 1 byte, we call it store byte, and so on and so forth, okay? So you kind of can see that this data is kind of a bi-directional thing. CPU can provide the data. Memory can also provide the data. If memory provides the data, we are loading. If you're writing to the memory, we are storing. Yeah, question? So the question is, if we store 1 byte, what happens? We're going to actually describe how exactly what. So remember, your memory is byte addressable, okay? So when I put the address, I put the address of the byte. I don't put the address of 32. So then that's why I won't overwrite other things. Okay. The second thing is the addressing, okay? How do we address the memory, okay? You can think about memory as a big array, okay? Starting from 0, let's say, to, I don't know, some big number, 1,000, okay? So essentially think about this is that if I want to write to this address, all I need to do is that mem of that address, and then I can write to that address, okay? So this is usually what we call direct addressing. We provide the actual address, okay? But sometimes you don't want to do direct addressing. Most of the time you want to do what we call base plus some offset, okay? Which means that I don't necessarily need to know the exact address. What I need to know is where is my base and where is the offset to that base. That would be my address. So for example, let's say, remember I told you that we have this thing called program counter, PC, okay? So PC is pointing somewhere in the memory, let's say this address. I can do, for example, PC plus 4, which means that 4 lines below this, and this is the address that I'm going to have, okay? So I don't provide the actual address. What I do provide is that you know what is PC, add 4 to it and write it to that address, okay? This is what we usually call base plus offset. So in this case, PC is your base and 4 is your offset, okay? And then you can replace this PC with any other register. So for example, you can do x1 plus 4, which means that whatever value x1 is storing, let's say, for example, x1 store is equal to 100. This means that the address that I'm going to write to or read from is 100 plus 4, okay? You're going to see why this is very important. In many, many cases, you will see that you don't necessarily need the absolute addresses, but you know the displacement or the offset of a particular address, okay? Another thing is that when we're talking about the address, this is what we call physical address, okay? There is another thing called virtual address that most of the modern CPUs are going to use, and we're going to have a full lecture on virtual address and what's the difference between virtual and physical. For now, whatever address that we are referring to are actual physical addresses. They're actual like addresses in the memory that we can go and touch, okay? The third thing is byte addressability versus 32-bit. So I already told you that registers are 32-bit, okay? But I told you that memory needs to be byte addressable. In other words, it needs to be 8-bit, okay? So there is kind of like a source of confusion here for many people that why my registers are 32, but my memory is only byte. The reason for this is that, as I told you, memory needs to be byte addressable for various different reasons. Most of them is for backward compatibility with previous systems, okay? That's why we kept our memory byte addressable, but we don't really want to have our registers byte per byte because we want to use parallelism, okay? So now the question becomes is that if I want to load into a register, what should I do? Okay, so if I want to read, for example, load something into X1, if I want to load word some address into X1, what should I do? Since every address is only 8-bit. In other words, what I need to do is that if this is my memory and this is line 0 that only has 8-bit, I need to read 4 lines at the same time so that 4 together becomes a 32-bit, okay? So when we are doing load word, what we are really doing on the memory side is that we are reading 4 lines at the same time. We concatenate them together and we send that to the CPU, okay? So, but if I do load byte, then I'm going only to read 1 line, that particular line the address is showing, okay? So now the question is that since I'm reading 4 lines, what is the address that I'm providing to the memory? Is it the address of the beginning? Is it the address of the end? Is it the address of each one? And then the answer to this is based on what we call little endian versus big endian, okay? So little endian is this format that if I have, let's say, a 32-bit number, which divided into 4 blocks of 8, okay? Where do I store the least significant bits? So let's say, for example, my data is, I'm showing it in hex format. So 0x, 1, 2, 3, 4, 5, 6, 7, 8, okay? So each of 2 is 1 byte. So this is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte. I'm showing it in the hex format. That's why every character is 4-bit. Each 2 characters is 1 byte, okay? So this is bytes, this is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte, okay? If you remember again from your M16 or CS33, we call this lowest bit least significant bit, and we call this highest bit most significant bit, okay? The highest bits, this is the highest position in your binary data. This is the lowest position in your binary data. Now the question is, where do I store each byte? I have 2 options. I can store 78 here, 56 here, 34 here, and 12 here. The second option would be I store 12 here, 34 here, 56 here, and 78 here. And this is address 0, this is address 1, this is address 2, and this is address 3, okay? So I have 2 different options of storing this. And there is no big difference between either of these 2. There are machines that implement one of them. There are machines that implement the other one, okay? This red one is what we call little endian, okay? Which means that I store least significant bit in lower addresses. So I store the first byte in address 0, the second byte in address 1, the third byte in address 2, and so on and so forth, okay? If I do the opposite, which is this blue one, we call this big endian, okay? Which means that I put bigger numbers in lower addresses. Little endian is more popular. It's mostly used in most of the systems. It's slightly more intuitive as well. You're kind of assuming that lower addresses means lower data, least significant data. So we're typically going to go with little endian. RISC-V assume that your machine is little endian, okay? So when we are storing this data here, essentially how we store it is that this red one that I'm showing here. Lower bits in lower addresses, okay? Any questions? Good. So when I'm reading a 32-bit, I'm essentially providing the lowest address, okay? So when I want to, for example, read this 4 bytes, I'm going to provide the beginning address here, okay? The address 0 in this case. So essentially, when I'm doing load word, what I'm really reading is I'm going to read address, address plus 1, address plus 2, and address plus 3. That's really what I'm reading because I'm reading 4 bytes at the same time. But when I'm providing the address, I'm just providing the base, the beginning of this system. And since this is little endian, I'm going to read it that way. Does that make sense? Yeah. Well, you always, so the question is that how do you make sure that you're not overwriting other things? So first, whenever you're writing to the memory, there's always the danger of overwriting things, right? But keep in mind that we're reading things in, like, let's say 4 bytes or 1 byte at a time, and we know what we're writing. There's nothing prevent you to overwrite things, and this could happen. Could be a bug in your system. But typically, when you're reading and writing from registers, you will see that you usually work in 4 bytes anyway. And you cannot, for example, you cannot start reading from this here. You usually start from like multiple of 4. So that's why you're kind of like always like reading 4 at the time. But to answer your question, it could happen. If your program, for example, has a bug, you can overwrite things. So there's nothing like kind of keep you from doing that. Any other questions? All right. So that's actually kind of very relevant to what you said. There's this what we call alignment issue. So typically, for example, let's say we have byte 0 here, byte 1 here, 2, 3, 4, 5, 6, 7. Okay? So this is it's a double word. It's 64-bit. Okay? And as I said, we are using little endian, which means that this is LSB, least significant B, and this is MSB. We typically read things aligned, which means that we read things in multiple of 4. So we typically read from here all the way to here, and the next read is from here to here, okay? But there's technically possibility that, let's say, if I want to read byte 3, 4, 5, and 6, and not 0 to 3 or 5, 4 to 7, I can do it. This is what we call misalignment, which means that I'm not really doing in consecutive of 4. Many processors doesn't allow you to do misaligned reads, okay? So it will throw an error to your system. Some other systems allows you, but what they really do is that if I want to really read 3, 4, 5, 6, this internally will be translated into 2 loads, okay? So it will read the first 4 bytes first, and basically discard these 3 bytes and only keep this one. Then it issue another load to read this other 3, and then combine the 4 bytes together to give you the data, okay? So in other words, it seems to be just 1 load, but in fact, it's actually 2 loads plus lots of shifting around in order to make sure that this works, okay? So in most cases, programmers tend to not do misaligned reads because that typically requires lots of additional hardware activity. But in some cases, this will not even happening because the system will throw an error. In some other cases, there will be some mechanism inside the hardware implemented to do the misaligned read. Okay? Just keep that in mind. All right. So as I said, there are different variants of store. So we have load word, load bytes, load high. We have also load bytes unsigned and load high unsigned. We have store word, store byte, and store high, okay? So the difference between them, actually, I think I have, okay, I don't have the table here. I'm going to go back to these, but just very quickly, difference between byte high and load word is the size. So load word going to give you, load word going to give you 32, load byte going to give you 8, and load half going to give you 16, okay? Load BU means that I'm going to load things unsigned. Remember I told you that if I read something 8-bit and I want to read it into a 32-bit, I need to sign extend it. So this first column do sign extension by default. So if I read 8 bits and I want to write it to a 32-bit, it will sign extend it. If I don't care about sign extension, I can do load byte unsigned, which means that I just read the 8 bits and copy it to the first 8 bits, and I don't care about the rest. Okay? In some cases, this would be helpful. Same for half, since you're only reading the 16-bit. For stores, it's slightly different. There's no notion of sign. So if I do store word, I read all the 4 bytes. If I do store byte, I only write to that particular system. So it's the programmer's job to keep in mind that the sign is correctly written. So if you're writing to the 4th, the most significant bit, you have to be careful about the sign extension. Okay? So you don't override the sign if you don't write it. Okay? But generally, that's kind of like the idea. So if I do store byte, we're going to write into only in one line of the memory. If I do store word, I write into 4 consecutive line of memory. Okay? That's the difference. Any questions about memory? Yeah. So the question is why store doesn't care about the sign. So for load, what is happening is that you have a register that is 32-bit, okay? And you want to load something to that register, okay? So if I do load byte, which means that I'm going to just read 8 bytes, and I want to write an 8 byte to a 32-bit, right? I want to write an 8-bit to a 32-bit, okay? So I will write the first 8 bits, and that's great. Now I have another 3 bytes that I need to decide what I'm going to do with it. Am I going to do zeros? I'm going to sign extend this number. What I'm going to do? That's why I need to know about the sign extension. Okay? For store is a different story. For store, I have the 32-bit number, okay, which is still the register. Now I want to write to the memory. If I write to the whole 4 bytes, then we're good. So we are writing a signed thing to a signed memory. So we're good. Now the question is that if I want to write only the first 8-bit, what should I do? So again, there's nothing to be worried about because when I'm writing store byte, I'm only writing into this first address. The other 3 addresses stay intact. So you already have those numbers there. Okay? If I want to write a sign extended version of this, what I would do is that I first make the sign extended into a register, and then I do store word. So this way, I'm going to write the entire thing that way. Yeah, question in the back? Yeah. Yes. So the question is, when you store the bytes, it's just the raw bits. Yeah, exactly. So you take the bytes and write it exactly to that byte. Cool. All right. So here's the operands. So how many operands do we have in RISC-V? We either have 2, we sometimes have 1, sometimes we have none. We don't have 3 operands in RISC-V. And as I told you, RISC-V is a RISC-based, which means that it's only one command and 2 operand at most. Okay? And then the question is, why not having 3 operands? Why not having 4 operands? Why not having many operands? And again, keep in mind that you can add more complexity to your system, but as you add more complexity, you're increasing the area, you're increasing the cost, and you're increasing the power. So there's always a trade-off. And that's why you choose the most optimum way. And in this particular case, 2 is the most optimal. Okay? All right, so let's also talk about commands, and this is a little bit more involved. Again, commands in RISC-V is usually just one type of commands, okay? We have 3 different types of commands in RISC-V. We have what we call arithmetic or ALU operations, we have memory operations, and we have control flow operations. So let's talk about them one by one. Arithmetic is, as the name suggests, doing arithmetic operations, takes 2 numbers, add them together, subtract them, multiply them, XOR them, OR them, etc., etc. There's actually a predefined list of the arithmetic operation that you can do. The arithmetic operations can happen between two registers or between one register and one operand. So you have two options for arithmetic operations, and usually you save the results into another register, okay? We usually call this what we call its destination registers, okay? The input registers are called source registers. The one that stores the final value is called destination register, okay? So there are like examples of arithmetic. I'm providing two here. For example, you can have a sub, which is a subtract instruction. What it does is that in RISC-V, you usually show the destination register first. So in this case, X3 is your destination register, and these are your source registers. So source register 1, source register 2. What this says is that X3 should be equal to X2 minus X1. So we read X1 and X2 from our register file, subtracting them, write the results back to X3, okay? As I said, you can have a register and an immediate as well. When we have an immediate, we typically add this I next to the instruction. So this one says that X5 should be equal to X1 plus 10, okay? So it reads one immediate, add it to the register, write the register, write the results back to another register, okay? As I told you, there is actually an actual table for this, so it's not like you can do arbitrary things. This is what is the standard. This is what RISC-V organization has approved, and this is what the compiler will understand and create, okay? So in RISC-V base edition, that's the one we're going to focus on, there are this many ALU operations, okay? So we have different things such as add and shift and set and XOR and so on, okay? What I'm showing you in this table is that this is what the command look like. This is basically these things that I showed you here. This is their actual kind of instruction that is happening. So this add-I, RD, RS constant. This is the description that what it does. And this is the kind of the mathematical equivalent of what is happening. So you can look at this table and hopefully understand what is happening in each one, okay? Let me break it down for you a little bit more. So let's start with add. So as you can see, we have two options for add. We have what we call add, which is ADD, and then add immediate, which is ADDI. The difference between them is that add takes two registers, RS1 and RS2, and store the results in RD, okay? So if you think about the mathematical representation of this, think about register as an array, a 2D array of 32 by 32. So it takes RS1 as the index, also takes RS2 as another index, add these two values, and write the results into RD as the index, okay? Question? So that's why so the question is that I said every instruction has two operands. How come this one has three? So that's why these two are the operands. This one is the destination. There is a difference. So we don't call RD as an operand. Operands are inputs to the system. RD is the destination. Yeah. Good question. So the question is, do we call RD as part of the command? Is it? So I told you this is not an operand. This is not the command either. It's destination register. Not every instruction has a destination register, but some instructions do have. It's not operands because it's not part of the input. It's not a command either. It's destination register. So that's what we're gonna call them. There was another question there, or yeah. Question is, could you add two constants together? And we don't. Do you know why? Why doesn't anybody wants to say why it's not a good idea to do two constants? Yeah. So yeah, so exactly. The reason is that if you want to add 3 to 5, you can start with 8 from the beginning. You are the one creating the constant yourself. You don't need to compute the constant. You are the one creating the constant. So you can actually start with 8, if that makes sense. But there are ways that you can actually load, and once you see a full program, you will see why you don't necessarily need to do 2 constants together. All right. So now the difference between ADDI and add is that, as you can see, you still have your RD and RS1, but instead of RS2, now you have your constant, okay? And if you look into the mathematical equivalent of this, is essentially RS1 plus some constant results in RD, okay? So that's with the add. If you look into other operations, you will see that mostly follow the same format. So you will see here that we have XOR, OR, and AND we have XOR I, OR I, and AND as well. And as you can see, for example, XOR follows exactly the same pattern as add. So there is an RD, RS1, RS2. XOR I has RD, RS1, and constant. The difference between them is the logical operation. So XOR does XOR, OR does OR, and AND does AND, okay? We also have subtract, okay? Subtract is also like this. The only thing about subtract is that we subtract this from this, okay? So the mathematical operations is RS1 minus RS2, okay? One thing to notice is that we don't have sub I. Can anyone say why we don't have sub I? Why do you think we don't have sub I? Yeah. Yes, so you can do add I with a negative immediate, and that becomes sub I, right? So there's no reason to waste another command for sub I when you can have negative constant. If you add a negative to a register, that becomes sub I, okay? You might ask then, why don't we have an add I with a negative? Then you need to have a negation command, which we don't have, okay? So you need to have at least one register that is doing the negation. Some instruction, some ISA has the not operation or negate operation. RISC-V doesn't have that. That's why they have the solve operation, okay? Questions so far? Yeah. Mm-hmm. Yes, the question is, since the constants are small, if I want to have a big constant, what should I do? You have to do it multiple times with some shifting and all. But you're actually going to get to it. Another question. All right. So continuing on, we have 2 other instructions. It's called shift right logical and shift right arithmetic. So shift means just shifting to the right or left. In terms of the format is also RD, RS, and RS. The only difference between arithmetic and logical is the sign, okay? When I'm shifting right, I'm shifting the sign bit, right? So for example, if I have 1, 1, 1, 1, and I'm shifting things to the right, let's say I shift to 2 bits to the right, I'm going to have 1, 1, these, so let's do it this way actually. So I'm going to shift these 2 guys to the right, so I'm going to have 1, 1. Now the question is, what should I put here? Should I put 0? Should I sign extend? There are 2 different options, okay? So basically, arithmetic and logical answer your question, okay? So arithmetic says, arithmetic says that you have to shift sign, which means that you have to sign extend. So you have to keep the arithmetic value of the number. Logical means don't care about the sign, just shift to the right, okay? So in arithmetic, what we're going to do is that we're going to sign extend here. But in logical, we're going to put zeros, okay? That's the difference between arithmetic and logical, okay? So we have SRL and SRA. The difference between those 2 is just the same. And as you can see, it basically says that the value of RS2 is the amount that we're going to shift. Don't be confused with the register itself. So we're going to have something like SRA, X5, X2, and x1, okay? So this does not mean that shift x2 by 1 bit. This means that whatever value that is stored here, this could be, for example, 7, I don't know, some number. It means that shifted that many bits, okay? It doesn't mean that shifted based on this index. Don't be confused by that. This is just an index to an array. The value that's stored in that array is the amount that you're shifting, okay? And of course, since these are 32-bit, shift more than 32 doesn't mean anything, right? So if you shift more than 32, you're basically zeroing these things out, okay? We also have shift left. Why don't we have shift left arithmetic? Anyone? Yeah, so shift left is shifting from left to right, from right to left. So essentially, this empty spaces would be at the beginning, and there is no sign extension for least significant bits. You always put zeros there, okay? So there's no difference between shift left arithmetic and shift left logical. They're all the same. So that's why we always have shift L. So we could have had like shift SLA or SLL, both of them do the same thing. So you basically shift the amount that is stored in RS2, RS1 by that amount, okay, to the left. All right. The last thing that we have is this thing called shift logical, left logical immediate. So it's their equivalent of this shift left, these things that we had before. This is the immediate version of that. So instead of saying that, go and look into the value stored in RS2, you say that just shift this much by the value in the constant, okay? So the immediate version of SLL, SRL, and SRA is the immediate version of that. Does that make sense? Okay. And finally, we have this thing called SLT and SLTU. This is called set less than and set less than unsigned. So what it does is it basically checks whether the two values in the registers are, the value of RS1 is less than value of RS2. If it is, it writes 1 to the destination register, okay? If it's not, it writes 0 to the destination register, okay? So it's, in other words, it's a comparison, okay? So if I want to compare the two values together, I'll check the destination register. If the destination register is equal to 0, means that RS1 was not less than RS2. If it was 0, then it means that this is less than, okay? And then less than, since this is a comparison, the comparison could be signed or it could be unsigned. So if it's SLT, it means that it's signed. If it's SLTU, it means that we compared just the values. We don't care about the signs, okay? So that's the main difference between the two. And of course, we have the immediate version of them. So we have SLTI and SLTIU, which is you compared RS1 with some immediate and then set the register based on that, okay? And you can have the signed and unsigned version of that as well. And that's pretty much it with all the arithmetic operations. Any questions from any of these instructions here? Yeah. Good question. The question is, can the register be both destination and operand? Yes. You can even have RS1, RS2, both same register, destination also be the same, if you really want to go all the way. Yeah. Any other question? Yeah. Yes. So when we are doing SLTU, we are just looking at the absolute values. Yeah. Can you store to x0? No. If you do a store in x0, nothing happens. You can write it technically here x0. It means that whatever happens, you just ignore it. So it's not going to throw an error, but nothing will happen. Yeah. Yes, the question is, all these instructions are mapped into hardware, and the answer is yes. Next week, we're going to actually show how. Yeah. Yes. Yes, so you can actually create, the reason for x0 is that you can create 0 easily, because then you can, for example, add x, you can zero out things very fast. By just adding everything to x0, you're essentially writing 0 to them, right? So that's why. Yeah. Uh-huh. No, so the question is that x86 has different variations with for different sizes and all. Does it exist here? No, that's actually the main thing about RISC, is that things are very small. So the number of instructions is very small. We only have like 50 something for the base, and everything is based off those. You don't need that many instructions. Okay. Um, so let's do like a very simple test for you guys. Let's practice. See if we can find the final value of x3 in this case. Yeah. Uh-huh. Uh-huh. If you do shift left, uh-huh. Uh-huh. It's already stored in 32-bit anyway, so you don't need sign extension. So you're comparing to 32-bit, you just ignore the sign bits. So you just look at the values as yeah. All right, anyone wants to answer? What is the final value of x3? Yeah. Okay. So, okay, so you can assume that, so we're going to start with this. So x1 after this would be equal to 3, right? X2 would be equal to 5. Then we're going to add x2 and x1 together. So x3 would be 5 plus 3 would be 8. And then we're going to shift right arithmetic x3 with the amount that stores in x1. So essentially, 8 is going to be shift right 3 bits, right? We're going to shift right 3 bits. So we're going to do 1, 1, 1, 0, 0, and all the way zeros. We're going to shift right 3 times. This should be equal to 0, right? Yeah. Oh, sorry. My bad, my bad. So 1, 0, 0, 0. This should be equal to 1. Good? Anyone has any question about this? Cool. This is another practice for you. Let's say we want to compute the sum of these array of 1, 6, 8, 9. And then we want to shift left it 2 bits and then subtract it with this 2-bit shift right shifted. So essentially, I want to compute this. And why is this? Okay? I'm going to let you guys do it yourself. Whoever wants can post it on Campus Fire. People can like it and you can get points. I'll give you like 2 minutes to think about it, and then we're going to continue. But the answer will be on Campus Fire. Yeah. I can't hear you. You need to show how the for works. I still haven't explained what is the control flow instruction, so you don't know how to work. You don't know. You're saying that can you create a for loop? No, no, no. You have to load it. Don't you need the address of what? No, no, no. You can use immediates. Create immediates with that. All right, let's continue on final slide. So as I said, someone post the answer to Campus Wire. We're gonna see, and let's see who can beat other people to it. All right. So last slides before I let you go. So this was all the arithmetic ALU operations. There's also two other instruction types, memory instructions and control flow. For the memory operations, as I told you, we have two basic operations, load and store. That's it. We're either loading things from the memory or writing things to the memory, okay? But as I said before, we have different sizes and types. We have word, which is 32. We have half word, which is 16. And we have byte, which is 8. We also have the signed version and unsigned version, okay? That's why we have W, H, and B, and we have U and basically nothing, which is the default is signed, okay? And as I told you, we have the addressing mode that you could either provide the base address plus some offset, or you can provide the direct address, okay? So these are the instructions that we're going to have. So we're going to have LB, LH, LW, LBU, and LHU. So this is byte, half word, word, unsigned, and signed. For store, as I told you, we're not going to have the unsigned version. We're going to only have SB, SH, and SW. And the way that we're going to address this is we're going to write it this way, okay? So we're going to write LB, for example, X3, and then we're going to put the offset outside. So let's say 8, parentheses, and then X inside. So X0, for example, okay? This is how we're going to write this instruction. So the way it works is that I'm going to use this as the base. In this case, X0 is the base, plus 8. This is my address, okay? I'm going to load from this address. Whatever value that is stored in this address going to be written into X3, okay? That's how we're going to do this. So for example, if I change this X0 to X1, the address would be X1 plus 8, and this value will be stored in X3, okay? For store, this is different. For store, first of all, this is RS2 and RS1. Notice that there is no destination register in store, and you're going to see this many, many times in this class. Store only writes to the memory. There is no destination register, okay? So the way this works is that the address is still calculated this way. So if I have SB, let's say X3, 8, X0, what happens is that I'm going to compute the address, and this would be the address. But I'm going to store whatever value is stored in X3 into this address. Okay, that's the difference. All right? You can take a look at these and pay attention to the difference between H, B, U, SB, and so on. So take a look at this sign extension, the way that we write to these addresses, and so on. So this is very, very important. Okay? All right, I see you guys on Thursday. I'm going to be a little bit late on Thursday, all right?